What's up, guys? What's going on there? In this video, we're going to be explaining how you can actually perform machine learning using 10 models. In this video, we're going to be doing several model comparison in machine learning. We're going to be using 10 different machine learning models to train an antimicrobial resistance data set and also a neglected drug disease data set. So what we're going to be performing in this project is going to be really very spectacular. We're going to also perform pipeline scaling. In addition to that, we're also going to save our model and then also feed our model with a kind of predictive data set for it to make prediction of what we have trained that model with. So by the end of this particular tutorial session, you should be able to understand how to train your given data set with several models. This is going to be ranging from the logistic regression model, the decision tree model, the random forest classifier, the gradient booster classifier. Then also we're going to be using the support vector machine and the naive Bayes model and others as well, the ones that we're definitely going to scale. So also outside of that, we're also going to perform some kind of we're going to save our best model and then call it for prediction when we pass in a particular given data. So in this particular video, I'm also going to show a very good evidence of object-oriented programming. Particularly, I'm going to pack all my models inside classes, and basically, if you really want to get very good with OOP, this is definitely that video that's going to show a practical application of object-oriented programming, particularly in terms of training our model and all of that. So I think with that said, let's get straight into the task for today. So I'm going to bring up my VS Code. This is what we're going to work with. And I'm going to save, I'm just going to create a file. So once you have VS Code installed and particularly running, so I've just created a folder and I'm going to call this the AMR data. Okay, so I'm going to call it AMR data. That stands for antimicrobial resistance data. Then I'm going to save it with the extension interactive Python notebook. Okay. All right, so that's it. Now, once we are done with this, the next thing we're going to do now is we're going to select our kernel, and for our kernel, we're going to be working with the Python environment, and yes, I'm going to choose Python 3.13.3. Okay, and that works very fine. Now, the first thing we're going to do now is we're going to import all the modules where we are going to that we're going to be using for this project, and we're going to be using the NumPy as NP. That's going to be part of it. And we're going to also import pandas as PD. Okay, and then we're going to import Pickle. Now I'm going to demonstrate something. I'm going to show us how we can save our model with Pickle and then also import it with JobLib. Okay, now basically we can work with just the JobLib module for this and also with the Pickle. Okay, but I'm just going to show us a kind of demonstration of both, and because here I should always be using one or maybe either of them, but I just want to leave that so that it's going to make a lot of sense how I'm going to save our model and also how I'm going to load it. Okay, I'm going to save with Pickle and I will load with JobLib. And then the next one we're going to do right now is we're going to now import that several features that we're going to be using to scale our model and also for our splitting. So we're going to go to the model. So we'll go to the sklearn package and we'll go to model selection. We're going to import, sorry, I'm going to use from, then we'll import the we'll import the train test split. Okay, from sklearn. Now we'll go to the pre-processing package and we'll import standard scalar, and then from sklearn.pipeline, then we'll import our pipeline. Now this is where we will now import all the models that we want to use in training, basically the modules that we use in training this model. So from sklearn, now linear regression, okay, model, so we're going to import. Okay, so linear, no, this is going to be logistic. Okay, and then from sklen dot we'll go to 3, we'll import the decision tree classifier. I think that's what we're going to work with now. Sklen dot so we'll go to the assemble and we're going to import the random forest classifier, and from sklen dot assemble we're going to import the gradient boosting classifier, and then also from sklen dot so we'll go to the naive bias. We're going to import, so definitely we're going to import the Gaussian naive bias, and then from sklen dot now we'll be working with the support vector machine, and so from svm we're going to import as the support vector classifier, and I think that is that. If there's any model that we are yet to particularly maybe bring in, I don't think there's anyone left. Probably we can add the key nearest neighbors classifier, so we can actually go from sklen dot neighbors. We can actually import as the going to the key neighbors. Okay, the key nearest neighbors classifier. And that works. So now for our metrics, for us to determine the metrics, because we're going to be really doing a lot of exceptional things in this video, where we're going to show us how to interpret our models and all of that. And we're going to actually go to sklen package for metrics, and we will import the confusion. First of all, let's start with the accuracy score from sklen.metrics. Okay, we're going to actually import the confusion metrics. We can always import all these together by putting a comma, but I just want to keep everything simple now. And we're going to import the precision score, and then from sklen we're going to also go to the sklen.metrics. So we're going to import our recall score. Okay, and these are all the models that we will need particularly for this project. Now the first thing we're going to do right now to get started is we're going to create a function, and this we're going to call it the generate data set, and instead of it we want to generate 1000, and then we're going to seed our port. So go random.seed. So basically what this does is that it's going to keep our data the same each time we run it. It's not going to change. And the next thing we're going to do right now is I think we can create the data frame. And how do we do that? Now to do that, we can actually say pd what's going to call our data frame. We're going to call it df. We'll call it pandas data frame constructor. And then instead of, we will pass a dictionary. So one of the first things we're going to have is we're going to have our age. It's going to come to the numpy random.round it. Okay. Then our age is going to be from 2 to 18 with our size at n. So okay. And the next one we're going to look at is we're going to look at our gene count. Okay, and that's going to be at np.random.roundInt, and it's going to be from 10 to 200. Okay, so we can set our size at n, and then the next one is definitely going to be our resistance score, and that is going to be np.random.round. So that's just going to be at n, because we basically want numbers like 0 point something, 0.1, and all of that. Okay, we want to generate random numbers, random floats more of. And then the next one there is going to be our, we'll look at hospital exposure. We'll look at hospital exposure, and that is going to, we're going to keep it at np.random.round it, and that's going to be at 0 and 2 with our size at n. Okay, And the next one we're going to do definitely is going to be our prior. We can look at the data frame, can look at prior antibiotic use, and that is going to be at np.random.rounding, and it's going to be at 02 size at n. Now, in addition, we're also going to look at our region, okay, and the region is going to be at, let's say, np.random.run. I think now we can actually choose the choice method. Now pass in east, west, north, south. Okay, size is n, and then the last one is going to be our seed. We can call this our maybe the bacteria strain. Okay, and then the bacteria strain is just one because we're trying to predict for a single bacteria strain. Basically, we're trying to make a prediction for a single bacteria strain, and this can be E. coli. Okay, so what we can do here now is np.random the choice. We can pass in that method properly, and then we have E. coli. Now, basically, this is it, and this is our data frame. We've got that, and the next thing we can do right away is we can decide to what we can now say now is that since we have our all our features, these are basically our features, we might want to now have our target, which is what we use to measure the ground truth to consider the target, and that is going to be our DF for DF resistant. Okay, now our DF resistant is definitely going to be what we can do now is it's going to be what's the criteria for us to have our DF resistant. So what we can do right now is we can, okay, I think I'm going to come off from this the frame block. So what we can do now to create our target, okay, we can try to wrap this inside of the function. We can try to create a function instead of this a nested function. We'll say this is to calculate, or probably I'm going to say to assign our resistance. Okay, I could just call it that. Okay, so what we are basically doing in this particular project is that we want to predict the AMR, that's antimicrobial resistance, okay, for a single bacterial strain. So more like what we want to get as our output when we feed in our data frame to the machine learning model is that we want to feed it in our features and then whether this is resistant or not. So more like resistant is going to be 1, as if it's resistant it's 1, if it's not resistant it's 0. Okay, so this is just basically what it means. If it's not resistant, then it is 0. Okay, so what we're going to actually do here now in this function is that we're going to actually have our gene, and then inside of here we'll have we can call it antibiotic, and another one I'm going to have here is I could say resistance. Okay, so these are actually 3 parameters that my function is going to take. I'm going to use a conditional. I'm going to say if the gene, okay, is greater than or equal to probably, let's say 30, or I can say maybe 40, because you know this is from random numbers from 10 to 200. So maybe we can put something like 50, and also probably our resistance is greater or equal to 0.6. That's for this. Okay, and we can also say our probably antibiotics, okay, it is let's say it is equal to 1. Okay, and then in that case, what is going to do now is it has to return 1, and else can actually say return 0. Okay, so that is just so it's going to return 0, but only if this condition is met. And now what we can now do now is that we can now to set our targets now. What we are now going to do now, we're not going to set for DF resistance, which is going to be our target. So we're going to actually say that is going to be df dot. So this is our data frame object. Our data frame, we'll now say we'll map it to, we'll call the map method, and then inside of it we'll pass no, we're going to call the apply function, and then inside of the apply function we're going to pass the lambda for r, and that's what we're now going to see. Inside of it, you can now call that function and now say assign resistance. Okay, now it will now be for the row of probably gene count, and for the row of what else? So that's going to be for the row of, second one is going to be for the row of resistance score. I'm trying to make sure I spelled that correctly. And so the next one is going to be for the row of prior antibiotic. Okay, I just want to spell that correctly. Okay, let me just copy that, and I think I can just paste that. Okay, so for the rule of antibiotic use, and yes, so that works very fine. And as usual, our axis is going to be equals to 1. I think that works fine. Everything is running, no issues, no troubles. Just to be sure, yeah, so that's just basically it. What we have done here now is that we have now created our data frame, and we've assigned what we need to do. And then the last thing we're going to do now is we are going to now return df. Okay, that's what we're going to do. Okay, so we'll return what? Our data frame. Okay, now the next thing we might want to do now is we might now want to probably do our encoding and splitting. Okay, now what we can call this now is we can call it prepared data, or we can call it processed data. I can just call this function prepared data. And basically what we're going to pass inside here is the data frame, and it's important for us to copy that data frame so that it doesn't really start misbehaving. Okay, because if you can actually just start by saying df blah 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 and all of that, and yeah, that's definitely not gonna work. And what we can now do right now is that if you look at these particular features here, now we see that we've got our bacterial strain, we've got our region, and all of that. So in order to prepare our, basically what we'll perform here is our feature and our target engineering. Okay, we're trying to prepare them, our feature and our target, which is our X and Y in machine learning, which is commonly used. What we can see now is that we need to pre-process our data. Okay, there are actually some of them that are coded in categories, and you know that those are actually not going to be able to pass in through the pipeline. And essentially what I'm going to do right now is I'm going to say df, I'm going to say region encoded. Okay, so I'm going to pass that to df. Okay, I'm going to say region. Now what we'll do now is dot map. Okay, that's to encode it, and I'm going to pass a dictionary inside of it. And what that means is that for east is going to be 0, for west is going to be 1, for north is going to be 2, and for south, so it's going to be 3. So basically we have now passed our, so we've now passed in our df, we've more like encoded our data frame in terms of region, which is already showing to be qualitative, right, or categorical. So, but now right now we made it quantitative. Now here, I think I forgot to pass size as n. I think I just did that. I just cited that right now. And the next thing we will now do right now is we are now going to actually perform that for our string. So I can actually say df dot string. So I could call it string encoded. Okay, so string encoded, I could go on to do that. But now, if you look at this particular data frame now, which is the bacteria strain, right? You see that we can easily drop this particular column, right? Can easily drop it and not have it captured. So what we are going to do now, instead of encoding it, because it's just our data frame is returning one particular bacteria strain. Essentially, what we can do right now is that we can actually say, okay, let's go on to perform our features. You can see that our x is going to be df dot drop. Okay, that is for our x. Now it's going to be df dot drop. So pass our columns. Sorry. Okay, that is the drop method. So pass our column, and inside of our column, we're going to have our bacteria strain, if I spelled that correctly, just to be sure. And I think the next one we will have to drop now, we will have to drop our resistance, because that is going to be in our target, and we can also drop our resistance. Okay, I think every other thing works better. Bacteria strain, in as much as it's is categorical, we are dropping it. It's not going to be part of our features. And our y is going to be df, definitely is df resistant. Okay, and then what we're going to return here, we're going to return our x and y. Okay, yeah, so basically everything works perfectly well. And I think at this stage now we've already prepared our targets and our features for our feature engineering. So the next thing basically we're going to do right now is to we're going to initiate a class, a blueprint. So that's where we're going to have our class, and instead of that, our class, we're going to instantiate. So we're going to name our class AMR training. Okay, I could just put that AMR training program. Okay, so that's what I'm going to call it. Okay, in our class, and if I'm not going to pass anything inside of that, so I'm going to create a method init. So I'm going to call init underscore init. Then now inside of this class, now I'm going to pass in the self keyword, our x and y. Okay, and then instead of this method, then the next I'm going to do now is I'm going to now pass in our self.x string, self.x test. I'm going to pass in our self dot this is going to be our self.y train, and our self.y test. Okay, so I'm going to assign this. Okay, so I'm going to assign this to our train test plate, and inside of it is going to have our x, y. Then I'll set the random state at 45, and then with the test size of 0.3. So what that means is that we're going to be using 30% of our data to perform our testing, and then 70% of our data to perform our training. Now, what it means now is that we will now begin to pass our methods now. So the first thing now is that we have our log train, now our logistic regression training without being scaled. And here we have our model is equals to logistic regression. We'll pass the maximum iteration. The maximum iteration is at 1000, and we're going to do model.fit, and then inside of it we'll have our self.x train, and inside of it we'll have our self.y train. Okay, and then we can now return our we can return our model. Okay, Now, alternatively, I can also perform our wipe here, but then I'm going to do that in our next video, how we can actually return several, several parameters as well here, okay, for particularly when we are running our classes. So they actually made different ways. So it's all about you using which of the ways that is quite very familiar and easy for you to perform your model training and all of that, okay? So essentially, what we're going to do now with respect to that is that we're going to actually define for our scaled, so we're going to call this our scaled logistic regression model. And as usual, we'll pass the self keyword. Remember, we're training 10 models. And then for model, we're going to go to call the pipeline, because here we want to pass it through a pipeline. And inside of this pipeline, we'll call our scalar. Our scalar is going to be the standard scalar. So pass that, we'll create the object, and we have our classifier, or you can also call this model if you wish to. Then we'll pass the logistic regression and then set our maximum iteration at 1000. Okay. Now the next thing we're going to do now is also going to create for our tree model. So we're going to call this tree train, and yes, as usual, pass the self keyword, and then inside of this self keyword now, okay, I think I actually got that correct. And then inside we'll pass our model. We can scale the tree based models. We can scale them, and then what we're going to do right now is we'll pass. So we're going to instantiate the object for the model, and that is going to be our decision tree classifier. And inside of it, we're going to pass our max depth as 4. And we're going to do a model dot fit. Okay, so pass our self dot x train, self dot y train. Okay, and then we'll now return our model. So the same thing is going to happen in our pipeline. So we'll go to do our model dot fit or self dot x train, self dot y train, and then we'll return our model. Now the next thing we are going to do right away now is that we're going to actually do for our random forest. So call it forest train. Okay, and we're going to pass in our model dot for model. Our model is going to be the random forest classifier, and inside of this now we're going to call our n estimators at 100, and we're going to see the model dot fit. We're going to fit it in. We'll see the self dot x train, and okay, self dot y train. Okay, it's going to return the model. So I think subsequently I'm going to be copying this so that we can actually stay out of any bug. And the next one is going to be our def. We're going to call for the gradient booster train. I'm going to call the gradient boost train. So we're going to call the pass the self, and we'll have our model is going to be equal to the gradient booster classifier. And I'm just going to copy this to save some time. All right, so now the next one we're going to do definitely is so we're going to call for that's the key nearest neighbors. So we'll call it neighbors train, and inside of that we're going to pass ourselves. Now this is going to be our model without scaling, so we'll call it the key nearest neighbors classifier, and inside of this we'll have our n neighbors. We'll set it at 5 and we'll fit the model. I think I'm just going to paste that, and that works very well. Now to scale our k nearest neighbor, so we've got the scaled neighbors train. Now we're going to actually pass our model into a pipeline. I'm going to call that pipeline method, and then inside of it, so we'll call our scalar. Sorry, our scalar is going to be the basically what we're going to pass in there. Our scalar is going to be the standard scalar, and then for our classifier, that's our model, is going to be the key nearest neighbors classifier with our n neighbors set at probably 5. Okay, that's how much it can iterate there. So the next one is going to be we're going to do for our support vector, and that's going to see our support. We're going to call it SVM train. I want to spell that well, and we're going to pass the self keyword, and then we're going to see our model is going to be equals to the sub SVM, that's the support vector classifier, and as usual we'll do our model.fit and self.xy train, x train, y train. Now the next thing we are going to do definitely is we're going to actually do for our naive bias, and we'll call it the naive we'll call that the naive train, and as usual pass our self keyword, and inside of that we're definitely going to have our model. It's going to be the Gaussian naive bias, and I think I forgot to pass in this here, and I think, yeah, that works fine. And as usual, I'm just going to pass this model.self.y train, x train as well, self.x train. Now we have about 10 models. We could count that 1, 2, 3, 4, 5, 6, train is 6, and we have 7, 8, 9, and yeah, I think there is no other one that we are missing out on. The scale, we can scale our support vector. I can do that. We could say our SVM scaled train. Okay, we're passing ourselves, and then we have our model. It's also called a pipeline, and then inside of the pipeline we'll pass something like a list, and we have our scalar to be the standard scalar, and we have our classifier to be the, definitely we're going to call it S, VC, and I think that's it. So everything is ready. We have our 10 models, and then before we go ahead, we just need to actually have a look on our 10 models. We have the logistic regression, classifier, whatever, training model, whatever you want to call it. And we have that one. We have the skill logistic training, regression training, and we have the decision tree classifier. We have the random forest classifier. That's the fourth one, and we've got the gradient booster trainer. We've got the key nearest neighbors classifier, for the skilled key nearest neighbors classifier, and also the support vector, as well as the support vector classifier, and the naive bias by the Gaussian naive bias. So I think all this is done. The last method we are going to leave is a method to perform our evaluation, and inside of this method we'll pass ourselves, we'll pass our name, and we'll pass our model. Okay, and we're going to actually explain how this function, this particular method, is going to take in parameters and what we're going to define inside of it. So basically here, this is where we're going to perform our evaluation, and aside from returning the model, we want to perform evaluation for our accuracy, the confusion matrix, the precision, and the recurse score. So first of all, what we can do here now is we can actually assign our y-pret to be our y-pret. What's our y-pret definitely going to be? It's going to be our model dot predict. Okay, and that's where we pass the self dot x test. Okay, and now for us to get our model, so because we passed in this particular parameter here, we'll have to now add our print statement, because definitely anytime we call this method, is going to print out whatever all the evaluation scores that we are performing. Remember that the ideal behind this video is that we want to actually make some kind of evaluation and prediction. Okay, so what we're going to pass inside of that method is going to be, we're going to pass in, we'll ask it to print. Okay, so inside of this, first of all, it's going to print our name. So we're going to pass in the name, okay, which is here, right? Just like we did for the model. I just want to know what's okay. So it's going to print our name, and then the next thing is here. It's we'll have our for our accuracy score. Okay, for our accuracy score, that is going to be, that's enter each time we call for our accuracy score. I'm just going to lock it inside of here. It's going to be our accuracy score. Then inside of it, we are going to, okay, to put the comma there, so that stays properly, and then another comma there. So for our accuracy score, we're going to have our, inside of this, we'll have our Y test and our Y breadths. Okay, and this same thing is going to happen for our confusion metrics. I'm just going to copy that, duplicate that, but here I'm going to call this the confusion matrix. So I'm going to explain what we mean by the confusion matrix in a jiffy. I'm also going to put that code again, but this time this is going to be for our, this is going to be for our precision. Okay, and that method, I'm going to change that to precision. Remember, we imported our precision score. Okay, then the last one is going to be our record score, and I'm going to have our record score. Then inside of it, we'll have our Y. I'm going to call the Y test, and then the Y breadths. Okay, so basically, this is basically what this model is going to perform, and I just believe that's quite very easy. Each time we call that method, that is definitely what it's going to return. And yeah, so the next thing we're going to do right now is that we're going to now start calling some of these some of the functions so that we can perform what we want to do. And then the first thing we will do now is we will now see for our, we can call that our AMR. You can say the data frame for our AMR, okay, is equals to the, I will call the generate data method. Yeah, and now remember, this is the first, this is basically the first function that we created here, right? And we said that it is always going to return data frame. So what we just did now is that we just assigned this is the data frame for antimicrobial resistance, right? So we assigned it to that generate data function. And then the next one now we have now is our prepare data method. So what we can now do now, since we have the data frame inside of it now, and that is returning x and y, so we can say x, y is still equal to our prepare data method, rather I'll say function, forgive me for that, and we'll pass our AMR data frame. Okay, so basically everything is running. I'll try to run that to see if there is any error. And what does it say? It says that numpy has no attribute random. Oh, I mistakenly misspelled. Where it was that? I'm just going to check that. Random. I'm just going to check where I might have spelled. Oh, see, it's here, that's here. So I said random. Okay, and I'm going to run that, and everything works perfectly well. Perfectly. So now the next thing we will now do now is that we will now have to create an object for this class, because in programming, anytime you instantiate any class, or probably want to instantiate it, you can't just call that by creating an object. So to call this particular class, it means that anytime we call this class, we'll definitely need to pass in these parameters, right? That each time we create an object for that class. So I'm going to call that, I'm going to call it program. Okay, I'm going to say it's equal to, I'll call the class, and I'm going to pass x and y. Okay, that's basically our target and our features. Okay, so you can actually recall here, okay, we created our target and our features. So the next thing now we're going to do right now is that since that we've created our target and features, we want to perform our model training. We want to train these models and then ascertain the one which is best for us. So what we can do now is that I'm going to create a dictionary because of this particular method that I fitted here. That's going to help me to code that. So I'm going to create a dictionary, and instead of that dictionary, I'm going to now pass so for logistic model. So that's going to take me to call that program. So I'm going to call program, then call the that's for the log train. Okay, and then for the next one, which is the next model, which is our scaled logistic. So I could say logistic model scaled. I could say logistic. Probably I'll say logistic model scaled. Okay, let me use proper programming terms. So I could say okay, logistic model scaled. I'm going to call the program method dot I'm going to call the scaled log train. Okay, and then the next one we're going to have right now is for our decision tree. So I'm going to say for our decision tree model. So I'm going to say the program, then I'm going to call that tree, and this is it. Okay, that works. So the next one is going to be for our forest. So I'm going to say random program dot. So I'm going to call the forest train, and I'm passing the method. And the next one is going to be for our that's the gradient booster. So I'll say for the gradient boost model, and instead of it I'm going to, as usual, call the program dot this is no, not that. It's program dot gradient booster train. Then the next one, that's going to be for our key nearest neighbor. So I'm going to say for our neighbors model, and I'm just going to call the program dot I'm going to call the neighbors training. Remember, we're looking at 10 different models, and then the next one, which is going to be the scaled, or I could rather say the neighbors model scaled. Okay, I could just pass in program as usual dot I'm just going to call this the scaled neighbors. I'll pass the method, and then the next one, remember, you can use single or double quotes, whichever one still works better. And then the next one after the key nearest neighbors, we have the naive bias, the naive model, and I'm going to pass the program, if that is the correct order, program dot the method, which is naive bias. Okay, so I'm going to add a comma there. And the next one is going to be our we can call that our support vector, the SVM model. Okay, so we can actually call that as program dot, that's the trained one, and then the scaled, I'm just going to use a scaled SVM. Okay, I think I feel like wrapping all of them in double quotes, just for us to have uniformity. And all right, so this is the scaled support vector classifier, and that is going to be program dot scaled, and that's it. So I think how many we do we have? 1, 2, 3. Is there any why is that? Why is that marking that there? I think okay. Oh, that's fine. So the next one we're gonna have right now is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have our 10 of our models. Now the next thing we will now need to do now is for us to now print out or get all of this model, we can actually do for, remember when we go back here, we called our name and our model. So that's the name and the model. So we can actually get back and say, okay, since we want to iterate over this dictionary, so for name, I could just title this models, okay? Model in models items, okay? So I'm going to call the evaluate and just evaluate. But as a program, okay, dot evaluate, okay, instead of name model, and that should run. Okay, what's the problem? It said could not convert float not. So we need to go back and understand why that is happening. Address that to say self dot y test, and say self dot y test again. We have self dot y test and self dot y test. So we run that, and perfect. So we get all our models, and so basically this is our models that we're using for the training without the accuracy. But for the sake of this video, I'm just going to give some kind of explanations. What this means here now is that based on all of these models, for logistic model accuracy score, we have the accuracy at 95%. For logistic model, that's for the scaled accuracy. That's for the scaled logistic model, we have accuracy at 96%. For decision tree, it's 100%. For random forest accuracy, it's 0.99.6, and that's 99.6 rather. And then for the gradient boost model, it's 100%. Neighbors, k-nearest neighbors is 81%. Scaled k-nearest neighbors now raised to 96%. The naive bias model accuracy is at 91%, and the confusion matrix is, you can see that. I'm definitely going to explain that. I'm going to explain for 2, then we can actually apply it to others. Support vector machine, that's for the support vector classifier, gave us 83% accuracy, and the scaled support vector gave us 98%, and also our so those are actually basically what we need to know. Naive bias is 91%. Now I'm going to show you something right now of what this entails, and how you can actually use it for what you want to do. But let me actually explain. Now, what I want to show you right now is that if you want to actually interpret this now, I can create a mark down here. I can actually say accuracy is at accuracy for, let's say, for logistic regression. That's for the scaled logistic. Let's just use for the scaled logistic model is at that is 96%, 96.6%. Now, based on our confusion matrix, that for the confusion matrix, now what this illustrates right now, now for our confusion matrix, what this illustrates, what it means, probably what it implies, is that we have something like this. I'm just going to show you something like this. Now we have something we call it, here is going to be the true negative, we have the false positive, we have the we've got the false negative, and we have the true positive. And now what we try to explain here is that, think about your confusion matrix as you've got this, I'm using for the scaled, so that's definitely going to be this. Okay, so whichever one, everything applies. Okay, so I'm just going to paste this down here now. So now what this means now is that now that we have our accuracy at 96.6, which is this, okay, Okay, what this implies is that during our check for AMR, remember we're interested in AMR, that's why I'm interested in knowing patients who've got AMR resistance, right? That's the resistance. Probably we're looking at the resistance. It could be whatever. But this is what we are looking at. This is what we are interested in, right? Resistant. So all right now. So now to interpret this confusion matrix now, okay. If we go up to our data here, you see that in our target, you're trying to feed in data that the machine learning models can now predict, okay, which of these patients, right, has AMR, probably E. coli, that's this bacterial strain, which of them is resistant. I think that's definitely going to be a very much more better explanation there. So what it means is that based on the prediction, 245 were true negative. So it means that I could say that for the true negative, this means that 245 of the of the patients, I could say 245 patients were accurately predicted to not have the what? That's to not have that resistance. That's what that bacteria, that strain resistance. That's what it means. Then based on our false positive, that's definitely going to be 4. Or can I actually say that 4 patients where we are wrongly predicted to have what? Strain resistance by the model, right? So remember, this is by the model. Okay, and now based on our false negative, we could say that 6 patients we are wrongly, let me spell that correctly, we are wrongly predicted to not have strain resistance by the model. And this is a very dangerous parameter. Okay, this is very dangerous because you're saying, okay, that these patients have this, whereas they don't. Or you say you're saying that they don't have this particular, because when you say false negative, those are basically the people who are usually in epidemiology, they are classified to not have it, whereas they do have it. Okay, so just like somebody shows up to your clinic and you diagnose them, oh, they don't have it, and they go on and continue to live, whereas they don't have it, and that can be very brutal. It's even better to say, okay, that you have it, whereas you don't have it. Okay, because medications at the end of the day is not definitely going to cure, but you know what it means to be false negative. So for true positive, I could say here that here it's more like the 45 patients were accurately predicted by the model, I could spell that correctly, to have this strain resistance. Now, I'm not really going to waste so much time. This is what it is. And now, one of the ways we derive our accuracy using this confusion matrix, we always say true positive plus true negative over our true positive plus true negative plus false positive plus our false negative. So basically, if you want to get this accuracy score here, we can actually say we sum up all of these. We sum up the true negative and the true positive and divide it by the sum of everything entirely inside of the set, and that's going to give us 96.6%. Okay, that's how we estimate for our accuracy. I'm just going to keep that here. So this is the formula for our accuracy. Okay, so now the next thing now is for precision. Now, what do we mean by precision? Now, we're trying to actually understand each time the model predicts one to have the disease, how accurate is it? So that's usually denoted as our true positive all of our false positive over our true positive. So more like when you look at this place now, each time the model says this person has this condition, how correct is it? And here we have our precision score as for our scaled logistic regression. We have it as 91%, okay, and that's 91.8 or approximately 92. So that's here as 91.8, okay. So 90% of 91%. So that means the model says that each time the patient is predicted to be resistant, it is what 91.8% sure. And this is actually a very important parameter whenever we come to epidemiological screening, because we want to make sure that our precision, we're very precise, and that's really going to give us we need high precision, because whenever there is limited resources, we don't want to waste some of our resources on people that don't have the condition of interest that we're looking at. And the next one we're going to actually look at now is our recall score. And then actually to get our recall score, that's giving us our true positive all over our false negative plus our true positive. And what the recall score means now, it tries to talk about how well was the model able to catch everyone that has the resistant strain, okay. And in this case, this is the formula, and from here we can actually see that our recall score is 88.2, okay. So that's 88.2%. So the formula is quite simple. Once you get 45, if you divide it by 45 plus 6, it's definitely going to give you 88.2%. So this is more like the explainability of the accuracy of our model, and I think that's quite very much important for us to actually understand in this particular session. So one of the things I might want to do now is before I go ahead to kind of create a neglected tropical disease data frame, and trying to basically compare that, use some of what we've trained in this model, or use our classes in this model to train it. I'm just going to show us what we call our feature importance and coefficient importance. So I'm just going to do that for 2. And basically, to do our feature importance, more like we want to get the magnitude of the effect of the features during the training, particularly for our tree-based model. So our tree-based models here is we have our decision tree classifier, and also we have our forest classifier, and they all give an accuracy of 1. So let us actually understand the feature importance of each of these models. So I could actually say our tree feature, or I'm going to say our tree feature importance. I'm just going to create a data frame for that. I'm going to say data frame, and inside of that, I'll pass a dictionary, and I'm going to say feature, and then basically that's going to be for the features. And I think what we can do, because we have our X and Y here, we can have our X and Y in a global variable. To get that, what we might do now, we might do something like X dot columns but I just want to be sure, I just want to list out what our features are, and yes, just put that in, and we can just, what we can do now is we can, because we need to bring that out as a global variable, so we can actually say our X is going to be our So we can actually pass in our age, and we can pass in our gene, and what else? What are other numerical variables we're more interested in? We can also pass in our resistance score, and I think those are actually the features we're interested in: hospital exposure and prior antibiotic use. Okay, and then our region encoded, so we can see our hospital exposure and then prior antibiotic use, and region encoded. So this is what our X is, and we can actually go down because we're trying to pass in some parameters, and we could just see, okay, but just try that out, and going to now call the model. So which of the model are we using for to get the decision tree, the feature? So I can come here and I'll say our tree model is equals to, I'm going to call the program dot tree train. Then I'll pass our tree model dot feature. Dot feature importances. I want to be sure, okay, except columns, also is so I can actually say I want to print my, okay, I want to print my, sort that. Perfect. That works. So this is what our feature importance is, and based on our decision tree classifier, and yeah, so we can actually do the same for our. We can still do the same for our random forest. And what I'm going to do here is I'm just going to change this to forest. Okay, remember these are our best performing models, and I'm going to change this to forest train. So I'm going to call this our forest feature importance, and I'm just going to change this to forest model, and this is our feature importance. We'll change this as well to forest feature importance, which is this, and I think that's just it. So can run that, and of course that gives us the parameters for our feature importance. Okay, so if we don't want to have this index in here, I could put dot to string, then I'll say index equals to false. Okay, and yes, I will have that index in there. So this is what our feature importance means. So it means that resistance score has a very high magnitude for the model during the training. That's basically what it means. And when you sum up all of this, it's definitely going to give you 1. Okay, that's what it means. So here now for our decision tree during the training, these are some of the features that had more importance, magnitude more like to the training data. Okay, to the training during the model training. So that's why it's arranged in this hierarchy. Okay, so I could still put the dot to string. I could actually say dot to string, and I'll put the index as false. Okay, so that works very well. So that we can just have a visual, maybe just kind of visual look at what it is. You see that hospital exposure, age, and region encoded had almost no significant impact on the training. So we have to now look at the model for forest model. For the forest randomized forest classifier, this is actually how important these parameters are. Compared here, antibiotic use was quite high here, but in our random forest classifier, you see that resistance score, which is the one that has much more importance, or much more magnitude. Now, what we can do here now is I can actually, for the normal logistic model score that wasn't scaled, I can actually check out the coefficient. Okay, so when we talk about the coefficient, we're trying to actually understand the direction of effect. Okay, we want to know the direction of effect. Now, I'm just going to show us something slightly. I think this is definitely going to be important. I've just actually prepared some kind of a note here I'm going to be using to explain. And in my other session, there was where I actually explained this properly. Now, this is what the confusion matrix looks like. Accurately, people who have the disease and all of that, but that's only the cause of this video. Now, what I want to actually look at now is just think about this now, because I want to explain the coefficient now. Now, we've got some of these parameters here. We've got age, gender, we've got water contact per week. And now, these are actually some of the inputs from the participants, right? And for gender, whether coded or not, we've got this. Probably this at the end of it when it's coded, it could be 1. Here it could be 1, and this could be 0. Okay. And this is water contact per week. And now what we're trying to actually explain basically, and this is the target, is we want to know the impact of these particular features on this particular patient developing AMR infection. So think about it as when you look at the age, let's say for example, it's minus 0.99. So what it means is that when you look at the number line here, still minus 0.99 shows that if it is on the negative, it means that it is reducing the risk of that target or the outcome. Now, if it's on the positive part, it increases the risk. Now, what this means now is that here now, being at negative here now, 0.990. So it means that it has a much more slight impact. Okay, I won't say slight, but that's around here compared to this minus 7, which is significantly going to reduce the risk of AMR infection. That water contact is really reducing the significance of what AMR infection compared to when it's on the positive. That's increasing. You see that for 0.02 marital status, it actually have almost no significant what impact in increasing the risk of what AMR infection compared to gender, which is very high, and that's here. So that is just basically what this is. I've made several explanations of machine learning explainability in my tutorials and all of that. So definitely go back to this session. And now what we will do right now is we'll jump back straight into VS Code, and here we have for our feature importance, we've done that already. So we're going to do for our coefficient. And what we're going to do right now is we're going to do the same thing for our logistic model. So I'm going to call that our logistic model. That's the one that wasn't scaled. Our logistic model. Now we're going to actually call the method program dot. That's going to be our. So this is our log training, and our feature still remains. Okay. So what we're going to do right now is we're going to call our coefficients data frame. So we're going to call it our coefficient. I can actually call it, if I can spell well, I could say the log coefficient df, the data frame. So create the data frame for that. So pass our constructor and instead of it a dictionary, and then we're going to have our here one of our feature, which is going to be our features. Okay. and we'll have our coefficients. Okay, so let's get the directionality of the impact, and we're going to have our, so we're going to actually pass our log model, okay, dot what we call the curve. Okay, so this is the curve, and inside of it we're going to pass something like this, and underscore I'll pass 0, which is basically for the first row. Okay, and we're going to now print so to print our log coefficient. Okay, so dot sort values, and instead of it to pass that method, and by we want to sort it by coefficient. Let's make sure you spell that correctly. And after sorting it like that, uh, I think that's that. Then we'll have our ascending as false. Okay, and I think we can print that. So basically it means that everything increases the what, so there is no negative value here. So age increases the risk of resistance, and essentially gene count slightly does, because if you look at this 0.00, so it means that age is definitely going to be here, slight increase. And then compared to, I think I'm going to drag this closer here, compared to resistance score. Okay, we have resistance score, which is one that significantly increases the risk of antimicrobial resistance and all of that. We've got prior antibiotic use as well, and like lots of them. Okay, so that's lots of it and all of that. So we've got hospital exposure region slightly does, gene count slightly does, and age slightly does, but all of them are actually increasing the risks. None of them reduces the risk. Okay, so that is that for our coefficient and our feature. So we can just do one more last one based on our scaled logistic regression. So I can actually do our scaled log model. So we're going to call that program dot, so we call our scaled log train, which return the model, and then we'll now see for our log scaled coefficient. So we're actually going to get that the data frame is equal to, we're going to pass the pandas data frame and then pass that constructor, and then instead of it we'll pass a dictionary. And instead of the dictionary, we're definitely going to have our feature, and then which is going to be our features. Okay, and then we also have our coefficient, which is going to be our scaled log model. Okay, I think that works. While we having that length there. Oh, we're supposed to pass a dictionary, and we passed them a list. Okay, all right, so yeah, that's fine. So what we're not going to do now is we're going to actually say that our log scaled df is equals to our, we'll call our log scaled df dot sort, and we have by, we're going to say dot sort values to say by the equal to coefficient. We want to check it when you scaled it, how the model performed, and we're going to actually have our ascending at false. Okay, I think we can now print our log scale data frame, and we'll print that. Oh, what's the issue? It said it's not supported for pipeline. Oh, sorry. So what we can actually add here, since this is a pipeline, so we've got this bug here, and to fix that, we're going to change this to CLF, and we're just going to run that, and that's it. So we get it. So what this means is that when you go back to our model here, when we're actually training that, you'll see that when we are scaling, we called it CLF. Okay, that's classifier. So that's our name step that we used particularly there. So this is basically what our coefficient means. And in the case of the scaled in the case of the scaled, that's when we scale the logistic regression data. We've got the prior antibiotic use. Now it's now at the top. So it means that using antibiotics severally all the time, it increases, antibiotic resistance, and yeah, that's it. So the next thing we're going to actually be doing right now, without wasting too much of our time, we're going to be creating a data frame. Okay, so we're going to you create an NTD data set, and then adopt our training model that we actually put in our classes. So I'm just going to create a function. I'm going to call it generate. Probably I could call this generate info, and yeah, so inside of it is going to be 800, and then okay, sorry, I'm just gonna end up with the full stops. Okay, and what we're going to do right now is np.random as usual. It's going to be at dot seed. It's going to be at 5, and now first of all we set our data frame, and we'll call this our df. Is going to be, now we can actually say the pandas dot, we'll call that constructor, and inside of it we're going to have several parameters. We'll have our age, we're going to have our, just going to say that's age, we're going to have age at np.random, and that's going to be from, probably we can do that from 4 to 60, and then we'll have we can actually call that, or whatever we can call it, put our n. Okay, that's the size, and yeah, now before we get into this, I think it's quite very important for us to, okay, so now that we are done with these coefficients and checking our features, I think it's very, very important for us to scale our data, right? Sorry, save our best model. And in order for us to do that, there are actually lots of things that we can do. But then let us continue. Let's continue with our data frame, right? So we'll go our df, and we can actually now see our, probably the next parameter there is going to be our household. We can actually say household contact, and I'm going to set it at probably that's going to be from, we can put that from 0 to 10. Okay, and remember that's wrapped around np.random.random, and that's going to be at there. Okay, that's the size. And the next one is going to be our treatment delay. So it could either be yes or no. np.random.randint, still you can put that at 0 to 20. Okay, whatever. And then the next one is going to be our hygiene. We can actually set that at probably we can keep it at, hygiene could be 0 and 2 with n, so that's fine. And the next one is going to be our target. So for us to set our target, we'll do the same thing that we've done. So in this case, I'm going to say our df dot, so our target is infection. Okay, so we can actually call that df dot this. I think I'm not going to wrap it in a function. I could now say df dot apply, and then I'll have the lambda function, lambda r. Then I'll now say it should give us 1. That's probably we can use the if statement. Say 1 if the r that's the row of age is greater than 40, or is less than, let's say for example, less than 25, and then the row of probably hygiene is equal to 1, and what else? What else you can see? Household contact is greater than or equal to 5, right? Greater or equal to 5, and I think those are actually okay, and you can actually see. Yeah, I don't think we should wrap this in it. Okay, I think this works better, and then we can actually see else 0. Then the axis is definitely going to be equals to 1. So I think that works fine, perfect. So this is it. So it's going to be 1 if it meets all these conditions, else it is 0. So now what's the next thing we're going to do right now? Remember, we're working with 800 data set. We can now create another function. So we're going to call this the pre-process, the NTD data set. Inside of it is going to be the data frame. Remember, before we leave there, we're going to actually return, because something has to be returned. So we return our data frame. Okay. Now, so inside of this preprocess, so one of the things we're looking at now is as usual, our df is equals to df dot copy. We'll have to copy that, and then the other thing that we're definitely going to do right now is, since we've copied that, we are now going to now say, okay, now for our df, is there any other value for us to encode or drop? I don't think so, but so it's our x, because all of them are basically in numbers. Now, so what our x is going to be now is going to be df dot drop columns equal to, we're going to drop our infection. Okay, then our y is going to be equals to df infection. Okay, so I think that's just basically it, and this function should return x and y, and yeah, we're good. So everything works perfectly well. And then the next thing we're gonna now do now is, since we've got our x and y, so instead of us to start training, splitting our data and all of that, we can inherit that other from that other initial class to train this. And what we can do now is, can now say here that we're going to call this our df ntd is going to be our we're going to say, ask it to let it generate the info. Okay, and then what we'll now say now is for our pre-processing, can now say our x. So instead of us to now call x and y, so it doesn't override what we've done before, we can say x ntd comma y ntd is going to be equals to our pre-process ntd with our df ntd inside of it. Okay, now the next thing we're going to do now is we're just basically going to call our models, and we don't really have to, remember, if we go up here now, we don't really have to start running all of this. I could go up a bit now. Like, we don't really need to start returning all these classes, yada yada yada, and all of that. So what we can do straight away is we can now call that method, right? But now we'll instantiate it with another. This time we'll call it training. Okay, we'll call it training is equals to AMR training program. Okay, and inside of it we'll pass our x ntd and our y ntd. Okay, Now we can call these our NTD models now, okay? Because we now want to create an object for each of these that we've called now, right? Because we instantiated an object training for this. So each time we're going to call this object and to print out what we want. So our NTD models, we'll save it inside of a dictionary as usual. So we'll call it, for here we're going to call it our logistic model, okay? So that is going to be assigned to the training dot our, so we'll call this method now, right? Training dot logistic log train, right? We'll run this cell again to be sure everything works perfectly without any error. Okay. All right, so we'll continue. So that's going to be that, and then for our scaled logistic training, or whatever thing you want to call it, or screen logistics, we're going to pass in our training dot scaled. So we just need to confirm that method from that class. Log train, scaled log train, scaled underscore log train. So scaled underscore log train. Now passing the next one. So this one now is going to be our decision tree. So our decision tree now is going to be our training dot is going to be our train. Okay. Remember, we are inheriting from this particular class. Okay, that's why we are calling all of that. We just created an object for this class, so passed in our own parameters and all of that. Now the next one is going to be for our not naive bias now, but it's going to be for random. So for a random forest, so our random forest training or model, whatever thing we want to call that, we can call that random forest model. I will call that training, as usual. We'll call our instantiator object dot that was forest train. Okay, now we can actually stop with what we have here, but if we decide to continue calling all that ones, we can. Yeah, so basically I just want to continue. I'm just going to call this this is going to be the gradient. That's why using the gradient booster now. When we use it on our model, I'm going to call this as usual the training dot gradient boost train. Okay, I'm just going to add a comma there. Now the next one is going to be our neighbors. So we call this the key nearest neighbors. So the neighbors model. So we're going to call the training dot the what? Dot the neighbors. Right, the neighbors train. Perfect. So it's beginning to pop out now. So the next one is going to be our. So next one is going to be our scaled. When we scaled our neighbors. So our scaled neighbors model is going to be our training dot scaled neighbors train. Now just to be sure this is correct, we can just go up and see. Okay, yeah, that's correct. That's it here. And we don't just want to make any mistake. And then the next one is going to be not scaled now. It's going to be our, after we've got our key nearest neighbors, the next one we have now is our we're going to have our support vector model machine is going to be, that's going to be our training dot s okay, no, that's not that, svm train. Okay, and then when we have our svm scaled, model, we're going to have our training dot our s. I think that is scaled. Just to be sure, I'm just going to confirm. Remember, repetition is going to give you mastery. Okay, that's a scaled before train, so scaled train. And I think I'm just going to correct that here. So that's scaled train. And then the last one is going to be our naive bias and naive model, and that is our training dot naive train. That's correct. And now 1 minute, I did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so there are 10 of them. Okay. Now, as usual, for us to print out each of these, for us to get our evaluation, we can actually say no, we can use the for name model in NTD models dot items. Okay. So we're going to actually do our training. So we'll call our training dot evaluate. So we call this method. So we just want to be sure that is what it is. Okay, evaluate, and we'll pass in our name and models. Okay, model, and we'll run that to be sure. Okay, it said that hygiene is not defined, and we want to know why. Okay, hygiene is not defined, and that is here. And also we'll have to correct that here. So I think that works fine. Perfect. So we've now used our model to train our class to train our NTD dataset, and the same thing still applies here. Here we've got an accuracy score based on that data of 92, but when it was now scaled, the logistic model accuracy was 94, probably showing some kind of improvement. And basically for our decision tree, we have 204 here, 3600, and all of that. So all these are still the same explanation that I have made before applies. And what we might do right now is we might want to save our best model, and then what I'm going to now show you now is how we can now use that particular model, like kind of load it and reuse it again. Then I'm going to show you how to calculate for your probability and all of that. So what we can do now is, based on this, right, our best performing model is our decision tree, which has a 1.0 accuracy. And basically what we can do right now to save our model, we can say our tree I can say our NTD tree model is going to be equals to our, we'll call our training dot train. Okay, so this is what it is. Okay, now how is it is now when we go up here? Okay, when we go up here, you'll see that when we initiated this method, we say that it should return model. So it means that if we are trying to now instantiate it with this object, we have to still assign tree model to that. So what we can now do now is basically we can now import, we've already imported Pico. I'm not really going to go back to that. So what we can do right now is, essentially, you want to do some kind of prediction with a given data set, right? And what we can do right now is we can now say, okay, let us save this model. Let's save the model. Okay, so how do we save this model? To save this model, we're going to use what we call a job leap. So we can actually say, probably to save it, we can actually say job leap, okay, dot dump. Then we'll now pass in the name of our model, which is NTD tree model, comma, then we'll have our, probably what's the name of the file. Name of the file could be, we can say decision tree model.pkl. Okay, and that's just it. So once we run that, automatically it saves, and this is our model. I also can inspect that by clicking on this and check it out on the text, and that's it. And now let's assume now that we have our model here. Now let's assume that I'm just going to open a fresh, and now also, yeah, this is our model. I'm also going to show us how to save our data frame. So to save our data frame, we can actually say NTD, we can say df NTD dot to CSV. Okay, we can call it our NTD data. Now we can say our NTD patients data. Okay, dot CSV. Okay, so once we click that, also it's definitely going to save. So you can see it has saved it. Now what I want to show us right now is I just want to show us how we can basically, we can also save this one also to underscore CSV. Okay, we can also save that one as well. We can say AMR, that's antimicrobial patients data.csv. So it's very important for it to add that extension. So yeah, of course, we've saved that as well, and that is it. Okay, this is for the AMR, this is for the NTD datasheet, and this is our model. Now, what we are going to do right now is I'm just going to create, now we're just going to look at this in terms of deployment. Let's say we've deployed this model, and we want to now use this model to train, to kind of give a prediction when we feed it with features, right? So that's what we want to do here now. So I'm just going to open here, I'm going to call it prediction.ipnb, okay, as usual. So this is just a new file. And essentially what I can do right here now is I'm just going to select a kernel, and yeah, I've just selected that kernel, Python 3.13.3. and how can I basically load that data set, right? So because now I want to just load a fresh data set, and that I want to not just load the data set, I want to load the model and pass some kind of data for it to make predictions. Okay, so we can now use what it's going to predict now to now say, okay, this is what our model has predicted. Now remember, when we go back to this initial data set here, when we go up, we find out that from our data set, for you to show resistance, it is 1. No, if there's no resistance, then that's 0. Okay, that's usually while we're doing supervised learning, and when we're passing data to the computer, what the computer is definitely saying is 0 is for no resistance, 1 is for resistance. Okay, yeah, so that's just basically it. So what I'm saying is basically for the interpretation of what I'm going to do. Okay, basically for the trainings, and just basically what we're going to do, the interpretation. So I'm just going to go back here, and what I'm going to do right now is I'm just going to call it the loaded, I'm just going to call that the loaded, probably what's going to be a best word to use for that. We can actually say our loaded model is going to be the job leap. So I'm going to call the job leap back again. This time around it's going to be .load, and I'm going to pass in the name here, which is decision tree model.pkl. Okay, and then what I'm going to do right now is since I've got this now right here, I'm going to now say that my prediction is going to be my loaded. Now remember, I just want to make this quite very clear, and probably I might just create a data frame. Okay, load model dot I'm going to say dot predict. Now inside of this, I could just create a data frame. I could call this age, and I could assign that at. Now we need to actually check out our features that we passed. We passed in age, we passed in household contact, treatment delay, hygiene, and we're not going to pass in infection, because basically this is what that's going to tell us resistant, not resistant, or whatever. But in the case of this, the model we saved for decision tree from our NTD. Okay, so what we're working with now is our NTD, right? So more like this is where we must pass in the exact features that was used in training the data. Okay, and I'm just going to come back here and I'm going to say, so the age I could assign it at 5. It must have to be in a list. And for the what next is there, household contact. Okay, just to be sure, I'm just going to say household contact. I'm going to pass that inside a list, and probably we can give it 6. Okay, and the next thing we're going to pass inside of there is we can pass in treatment delay, which is ranging from 1 to 20, and I can actually pass in treatment delay. So I can pass in 13, and then the last parameter is I'm going to pass in there is hygiene, and I could say probably 1. Okay, so I can say hygiene. So I could say hygiene is 1. Okay. Now, what I'm going to do right now is this. I'm just going to print predict. Now, prediction. Now, this is going to, let's see what happens. Okay, it said that job lib is not defined, and that is because I didn't import that here. Sorry about that. I'm going to import job lib, and then I'm going to import pandas as PD. Now what I can do now is I think we can pass all of this inside the we can call it data is equals to pandas bd dot data frame, and I think I can just pass that in. I don't have a nested dictionary, and then it's going to predict data. Okay, so when we run that, that should give us our prediction. So it's running. Okay, it says that features unseen at fit time, treatment delay, and yet it's missing. What was the issue? What's that? And what we can do, okay, treatment delay was not added. Is that what it's saying? I just to be sure I spelled that correctly. I could just confirm. Oh, there is a mistake there, and I think we have to correct that in our data sheet. And okay, we didn't. Oh, this is where we have the problem. Okay, we put in dash, and so I'm going to correct that, and that went through as well. And I think we can do away with this, and then we'll save another one, and everything works. Now, if you look at this CSV here, you see that there are numbers here indexing. If you don't want that to be present, what you can actually do is dot to comma index equals to none, and also do that here, index equal to none, and automatically that's, we're just going to run this as well, so we can check our AMR data sheet, and yeah, it's gone. So that's clear and clear. So we'll go back to our prediction, and I think we've sorted that out, and automatically should run, and that's very correct. And we have 1. Okay, so what that 1 implies now is that when we pass this particular patient data, this singular patient data here, our model has now predicted it to be what? Correct. Now, what about if we want to know the probability of our prediction, on both sides? Whether is it going to, how much is it saying, okay, it is 100% accurate or not, or something like that. Okay, so what this is going to be right now is we're going to have this equal to probably we'll say our loaded model dot predict log proba. Then that's going to be proba, and we'll pass in our data here as well. We can actually print our probability. And that tells us that it is 0%, 0, 1, right? So that means that 1% it is like 100% accurate. So that's it for this lecture. Thank you very much for your time, and I'll see you in the next one. Bye.